This is your presenter, Asloob Mudassar, and I am presenting slide number 13E of the course on atomic and molecular physics. Today, I shall be covering the following topics: double resonance and optical pumping, measurement of splitting of states in Z-man effect as an application of the double resonance method. This is a last lecture of the series of slides E, in which the external magnetic field is applied to the atoms. Double resonance and optical pumping. Brazel, Beater, and Kassler in the year 1949 to 1952 reported double resonance method and some experiments. So here we are going to present two different experiments will be presented for the measurement of splitting states between splitting states of the Zeeman effect using the double resonance method. So for the first method, I am going to choose the mercury atom. So for the mercury atom, the value of Z is equal to 80, and the electronic configuration is 1s2, 2s2, 2p6, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, 4d10, 4f14, 5s2, 5p6, 5d10, 6s2. So the ground state of the mercury atom is 6s2. This 6s2 can be written as 6s6x, where for the first 6s I have L1 is equal to 0, S1 is equal to half, and similarly for the second 6s state I have L2 is equal to 0 and S2 is equal to half. Where S1 and S2 are the spin quantum numbers related with the 6s electrons, and L1 and L2 are the orbital quantum numbers related with the 6s electrons. Now, to calculate the total quantum number of the system, I have capital L is equal to mod of L1 plus minus L2. So mod of 0 plus minus 0 is equal to 0. And now I am going to calculate the total spin quantum number. Capital S is equal to mod of S1 plus S2. And here I have a mod of half plus minus half is equal to half minus half is equal to 0. So you see that the negative sign has been chosen over here, and the spin, because in the ground state, the electrons would be in the anti-parallel state, because I have the same subshell. 6s is the subshell, and when you have the same subshell, then if there are two electrons, the two electrons would like to be in the anti-parallel configuration, anti-parallel spins. So I have a half minus half is equal to 0. And the two electrons as shown by the red arrows are in anti-parallel state. And this is the total spin quantum number of the atom or the electrons. Now the total angular momentum J of the atom is given by mod of L, capital L plus minus capital S. And you know that in both of these, I have the value of capital L is equal to 0, capital S is equal to 0, and then the total value, and then the J is equal to 0. And the multiplicity is given by 2 times capital S plus 1. And since capital S is equal to 0, the multiplicity becomes equal to 1. So the ground state term configuration can be written as 6, 1s naught or 1s0, where 6 represents the principal quantum number, 1 as a superscript before the symbol S is the multiplicity, and this 0 is actually the total value of the quantum number J of the atom. So the ground state is represented by 6, 1s0. Now I am going to consider the next excited state for the mercury atom. So from the 6s2, one electron will be moved as the p electron. So now I have two electrons. One electron is in the 6s state, the other electron is in the p state. So since these two electrons are now in opposite subshells, so what will happen there? The two electrons will like to have parallel spins. And you know that when these two electrons will have the parallel spins, then of course the atom will be in the energy state with minimum energy. So for the 6s electron, I can write L1 is equal to 0 and S1 is equal to half. S1 is equal to half for the case of single electron, and similarly for the 6p electron where only one electron is present, I can write L2 is equal to 1, because for the p state the value of the orbital quantum number is 1, and the spin quantum number is again half because of the presence of the single electron in the 6p state. Now the total angular moment, the total quantum number, orbital quantum number L is equal to the mod of L1 plus minus L2, and substituting these values of L1 and L2, I get the total value of the total angular total quantum number L is equal to 1. And similarly for the total spin quantum number S, I have the expression is equal to mod of S1 plus minus S2, substituting the values of half plus minus half, I have two possible values 1 and 0. So here I am going to choose a value of 1 for the parallel spins, because for the in the parallel spins I have chosen because the two electrons are in different orbits, that is in the C in the 6s state, and the other electron is in the p state, so the electrons will have parallel spins. And this is as per Hund's rule of maximum multiplicity. The energy is minimum when the electrons have parallel spins. So you see that we want the excited state to have the minimum possible energy state, and this is only possible when the two electrons have the parallel spins. And according to Hund's rule, the two electrons will be in parallel configurations. That is, their spins will be parallel to each other. Now the total angular momentum, the total quantum number J of the atom is equal to mod of L plus minus S. So I have chosen only capital, I have chosen capital S is equal to 1 over here shown in red. So I have mod of L plus minus 1, and there are three possible values 2, 1 and 0. And you know that the multiplicity is equal to 2s plus 1. So since I have chosen only 1 as the red value, capital S is equal to 1, I have chosen this value, and I have explained why I have chosen capital S is equal to 1. So substituting that value over here, the multiplicity becomes equal to 3. When the multiplicity is 3, it means that three different values of the total quantum number J of the atoms are possible, and that's why I have three different values 2, 1 and 0. When 1 plus 1 add, I have 2. When 1 minus 1 are subtracted, I have 0. And in between, the integer possible values is 1. So 2, 1, 0 are the three values for the total quantum number J of the atom. Now you see that I am regarding the first excited term as 6,3p1. That is, I am choosing the total quantum number J to be equal to 1. Why I am choosing this state? The reason is what I am going to explain in the next paragraph. In an excited state, whenever possible, the two electrons will have parallel spins. As I have explained that I have chosen capital S is equal to 1, and 1 is the case when the two electrons have the parallel spins. There are three values of capital G, which are 2, 1 and 0, and thus three excited states are possible. And the three excited states will be 3p2, 3p1 and 3p0. But I have only indicated that the first excited state is 3p1. So there are three values of J, and thus three excited states are possible. But here the excited state shown is of interest, and the other two excited states are the metastable states. That is, their lifetimes is much larger. More detail about the LS coupling will be given in some other lectures. So you see that the other two states, which are the 3p2 and 3p0 states, are the metal stable states. And here I am not going to choose the metal stable states. I am going to choose only the state which is non-metastable, and that state is 3p1. Because for the optical pumping, the 3p states, which is a non-metastable state, is the required state to be discussed. The transition from the ground state, which is 6 1s0, to the next to the first excited state, which to the possible excited state for optical pumping is 6 3p1. And these are the resonant states, resonant transitions. That is, the transition from 1s0 to 3p1 is possible, and also from 3p1 back to 1s0 is possible optically. So these two states are referred to as, and the transition between these two states is referred to as the resonant transition, with wavelength is equal to 253.7 nanometer. In the presence of the external magnetic field B naught, the mercury atom are excited to Mg is equal to 0 level of the 3p1 excited state using a linearly polarized light in the pi transition. So you see that this is the state that is from 6 1s to 3p1. The transition will give you this wavelength, which is 253.7 nanometer. And this is the resonant transition. That is, you need this wavelength for excitation from 1s0 to 3p1, and similarly the same wavelength will be emitted when the transition from 3p1 to 1s0 takes place. And this is the transition in the absence of the magnetic field. So when you apply the magnetic field, the levels are split into the Zeeman effect, into the Zeeman level. That is, we are applying the moderate value of the magnetic field B naught. Then you see that we shall have the Mg levels corresponding to 3p1, because since we have 1 over here as the subscript with the 3p1, it means that we have chosen capital J is equal to 1. So when capital J is equal to 1, then under the application of the external magnetic field, there will be 3 possible values of Mj. So Mj will be equal to 0 plus minus 1. That is, with the application of the external magnetic field B, the J degeneracy is lifted. In the when the magnetic field is not present, then J is equal to 1 will be only a single level. But when you apply the magnetic field B naught, then the J is equal to 1 level will be split into 3 levels. That is, the J degeneracy is lifted, and the Mj levels will be equal to 0 and plus minus 1. That is, the 3 values of Mj will be possible. And we shall consider the Mj is equal to 0 level for the excitation from the ground state, which is 1s0. And you know that in the ground state, which is 1s0, the value of capital J is equal to 0 in this case. When capital J is equal to 0, then of course under the application of the magnetic field, there will be only one value of Mj is equal to 0. So the ground state 1s0 under the application of the magnetic field has only one Mj value, which is Mj is equal to 0. Whereas the 3p1 level under the application of the magnetic field will have 3 levels, that is Mj is equal to 0, Mj is equal to plus 1, and Mj is equal to minus 1. So from the ground state, which has only one level, Mj is equal to 0, we shall carry out the transition or the excitation from the ground state 1s0 to the Mj is equal to 0 state of 3p1 using the linearly polarized light in the pi transition, in the pi configuration, where pi means that the electric field of the linearly polarized light is parallel to that of the applied magnetic field. So in the transition from 3p1 to 1s0, transition gives back linearly polarized light in pi mode. Because this transition is, that is a resonant transition. So the same light which is used to excite the level from 1s0 to 3p1, the same light is emitted when the transition from 3p1 to 1s0 takes place, and the same light, that is the pi light, will be emitted. Now transitions delta J is equal to plus minus 1 can be induced with a high frequency coil perpendicular to B naught as shown. So you see that this sentence I shall explain this sentence in much greater detail, but after going through this diagram. You see that in this diagram I have a cavity that contains mercury atoms or the mercury vapors. This cuvette contained between the two magnetic fields contains the mercury vapors or the mercury atoms. And I have applied a magnetic field B naught, which has been shown by the coils, by the red coils. Red coils are the electromagnetic coils which generate the magnetic field B naught. And then I have another coil which is shown in green, and these green coils generate the magnetic field B1, and the magnetic field B1 is perpendicular to the magnetic field B naught. The magnetic field B naught or the coils of the B naught generate a magnetic field, and this magnetic field B naught is actually used for the Zeeman splitting. That is the level, that is the value of capital J will be split into mj levels under the application of the moderate magnetic field B naught. But there is another magnetic field due to the coils of B1, that is the magnetic field B1, which is perpendicular to the magnetic field B naught, and B naught is also applied to the cuvette containing mercury atoms. This magnetic field B naught is a high frequency magnetic field B naught that can be used to induce further excitations in the levels of the Zeeman levels of the mercury atoms. So B naught will be used to generate the Zeeman levels for the mercury atoms, whereas B1 will be used for the excitation or for the de-excitation of those mercury atoms within the, and this excitation will be done within the Zeeman levels. So you see that I have shown for the mercury atoms, I have shown the excitation with a pi light. So the pi light, which is a linearly polarized light, and this linearly polarized light has an electric field parallel to that of the magnetic field B naught. So you can see that the incident light, which is shown with the two electric fields, and is a pi light with the electric field parallel to that of the magnetic field B naught, is incident on the cuvette containing mercury atoms. So the mercury atoms will absorb the light, and the light will be used to excite the level, to excite the mercury levels to the mj is equal to 0 level. That is, we shall carry out the excitation from the ground state 1s0 to the mj is equal to 0 level of the 3p1 state. That is, pi light will be used to excite the central Zeeman will be used to excite the central Zeeman effect of the 3p1 state. And when this level is excited, that is the mj is equal to 0 level of the 3p1 state is excited, then the magnetic field B1 can be used to further excite mj is equal to plus 1 level, or mj is equal to minus 1 level can be excited using the magnetic field B1. So you see that when the mercury atom will absorb the light, pi light for the excitation, it will also re-emit the same light. That is, the pi light will also be emitted. And again, for this pi light, the electric field is again parallel to that of the applied magnetic field B naught, as shown over here as an exit beam. That is the beam coming as the emitted beam from the mercury atoms. You see that in this diagram, I have also shown the emission of sigma light. And you know that sigma light is a circular polarized light when observed from the direction of the B naught. That is, along the direction of a B naught, you have this electric field. This is the sigma light, which is a circularly polarized light, and the light in the sigma light has an electric field which is perpendicular to the direction of the magnetic field. So in the sigma light has electric field perpendicular to the direction of the magnetic field B naught, whereas the pi light has an electric field parallel to the direction of the magnetic field B naught. So now I have given you that how this picture will work. That is, what is the role of B naught. B naught will be used for the excitation of the level of the for the splitting of the Zeeman levels, whereas the B1 magnetic field will be used to induce excitation among the Zeeman levels or de-excitation among the Zeeman levels. So B1 will be used for the excitation or de-excitation of the Zeeman levels, whereas the B0 is used to generate the Zeeman levels, and this is what I shall further explain using the spectra of the corresponding spectra from the mercury atoms. So Hg atoms are contained in a cavity which is placed in a constant magnetic field B0 and also in a high frequency field B1. And I have explained the role of B0 and B1. So let me explain this figure first and then I shall explain the relevant text. You see that I have shown the 3p1 level and 1s0 level. These are the two levels represented by single lines. And these levels will represent single lines in the absence of the magnetic field. So when B0 is equal to 0, the 3p1 level and the 1s0 level will be single levels. And the transition between these two levels will give you a wavelength of 253.7 nanometer. The same wavelength can also be used for the excitation, and the same wavelength will also be used in the de-excitation process. That is, these two levels, 1s0 and 3p1 levels, are the resonant levels. Now you see that I am going to apply the moderate value of the magnetic field, which is used for the splitting of levels, single J levels into the Zeeman levels. Since you see that the value of capital J is equal to 1 for the 3p1 state, so when J is equal to 1 and you apply a moderate magnetic field external constant magnetic field B naught, then the J degeneracy is lifted and we have the three levels split into mj levels. So mj will have three values, plus 1, 0 and minus 1, because the value of capital J is 1 and the possible values of mj will be equal to 0 and plus minus 1. And I have shown these in energy wise, I have shown their distribution, that mj with plus 1 has the highest value, then follows by mg is equal to 0 and then followed by mg is equal to minus 1. And you say that I have indicated these levels in the presence of the applied magnetic field B naught. But you know that the ground level, which has J is equal to 0, this level will not be splitted under the application of the magnetic field B naught, because J is equal to 0 means that only one value of Mj is possible, which is Mj is equal to 0. And you see that here I have indicated Mj is equal to 0 level, which is the same original level of the 1s0 level. Now, in order to excite the mj is equal to 0 level of the excited state, I am using the pi light having the same wavelength as lambda is equal to 253.7 nanometer. And this is a linearly polarized light used in the absorption or in the excitation. And this light is a linearly polarized light with its electric field parallel to that of the applied magnetic field, as I have indicated in this diagram. That is, the pi light has an electric field parallel to that of the applied magnetic field B naught. So you see that I have excited mj is equal to 0 level of the upper state. Now you see that I have shown this frequency nu over there. That is the separation between the other mj levels with respect to the central level is in terms of energy is given by h nu. So if you provide energy, an additional energy through the magnetic field B1, then you can excite the mj level from mj is equal to 0 to mj is equal to plus 1 by using the magnetic field B1, because the magnetic field B1 will provide you the quanta of energy in the microwave region, and this quanta of energy is given by h nu. Notice that the splitting of states is constant in this case. because this is the case of the ordinary Zeeman effect. Because in the ordinary Zeeman effect, you know that the spin magnetism is zero there, and then of course we have this, and so you see that the spacing between the levels is the same. And similarly, I have shown the lower level, which is mg is equal to -1 level there. So I can also use the B1 magnetic field in order to induce the lower transition. That is, I can induce the transition from mj is equal to 0 to mj is equal to -1 level, again using the magnetic field B1. So it means that I can excite from the pi transition, I can excite the mj plus 1 level and also mj is equal to -1 level. So when the mj is equal to +1 level is excited using the microwave from the B1 field, and the excitation is done from mj is equal to 0 to mj is equal to +1 level, then of course this mj +1 level of the upper state can decay to the ground state mj is equal to 0. And this is what I have indicated by the red arrow. And this is the sigma plus light. And sigma plus light, you know, that is the circularly polarized light as observed from the direction parallel to B naught. So mj is equal to +1 level will decay through the circularly polarized light indicated by the longer green arrow to the ground state with mj is equal to 0. And the difference of the delta mj for this transition is equal to +1. +1 is the value of delta mj, which occurs for the transition of mj is equal to +1 to mj is equal to 0 of the ground state. So I have also indicated another green arrow, that is the transition from a -1 level of the upper state to the ground level of the ground state. So the transition from mj is equal to -1 to mj is equal to 0 of the ground state is shown by the second, that is a smaller green arrow, and the transition is represented by sigma minus. So sigma plus and sigma minus are both the circularly polarized light when viewed in a direction parallel to the direction of the magnetic field. But you know that these sigma lines contain electric field which is perpendicular. This electric field in the sigma light is perpendicular to the direction of the magnetic field. And this is also I have shown over here. So you can see that the emission of sigma line is shown as a circularly polarized light with an arrow. And of course, this arrow has a circularly polarized light in which the electric field of the circularly polarized is perpendicular to that of the direction of the magnetic field B naught. So you see that consider the resonance level. For the resonance, you see that there is an absorption. Pi light is absorbed and pi light can be re-emitted, because the other levels, that is the levels 1s0 and level 3p1, are the resonant levels. Same wavelength is absorbed and same wavelength can be emitted, and the emitted wavelength is shown in dotted lines, in the dotted red lines by the red line transition. So this is the transition if you apply the magnetic field to the mercury atom, or if you don't apply the magnetic field to the mercury atom, this red transition, that resonant transition, will occur between the 1s0 level and the 3p1 level. So the two levels, that is the solid red level used in the absorption and the dotted red level shown for the transition or for the emission, will occur between these two resonant levels. So I am not talking about here the red line in dotted, I am talking about the solid red line used in the absorption, and the other two light brown light brown transitions used as the excitation of the Mj is equal to +1 level, and as the de-excitation of Mj is equal to -1 level using the applied magnetic field B1. And the h nu quanta is provided by the magnetic field B1. So you see that there are two possible transitions, sigma plus and sigma minus. So if you could measure sigma plus and sigma minus using these two transitions, you can measure the separation in terms of energy between these two states. So you see that you will keep on tuning your microwaves, and when the microwave signal matches with the energy separation between these Mj levels due to the magnetic field B1, then what will happen? These transitions, that is sigma plus and sigma minus, will take place, and the ground population will increase. When the ground population will increase, then of course using the absorption spectroscopy you can measure there is an increase in the population of the Mj levels, and through that one you can notice that something has occurred extraordinary, which means that the microwave energy has matched with the energy levels of the Mj levels of the upper state of the 3p1 level. And when this transition occurs, then of course the population of the ground state will increase. And of course by measuring these sigma plus and sigma minus, which is now possible, then you can measure measure the value of the microwave energy, which matches with the energy difference between these two, between the Zeeman levels. So the separation of energy between the Zeeman levels can be determined very accurately. But you see that I shall describe now in the today's technology, it is very easy to perform such experiments, and very precise experiment and very precise excitation can be done using another laser. That is the excitation of the Mj plus level and Mj minus level can be done very precisely, and then of course the very precise separation between these levels can be measured very easily. But you know that I am going to describe this historical experiment, the experiment that was done in the history. So I am going to explain that one. So let me go through first the first paragraph. Although I have explained that one, so let me go through the paragraph so that the things become quite clear. The Zeeman sublevels, which are Mg is equal to +1 level and Mg is equal to -1 level, are thus populated. And these two levels becomes populated under the application of the magnetic field B1, which provides an energy quanta equal to h nu. The light emitted under the transition from Mj is equal to +1 of 3p1 level to Mj is equal to 0 of the ground level, and then again from Mg is equal to -1 level of 3p1 to the Mj is equal to 0 level of 1s0 are circularly polarized lights represented respectively by sigma plus and sigma minus respectively, which are circularly polarized lights. So you see that with when the Mj +1 and Mj -1 has some population in their levels, then of course these populations will decay optically to the ground states emitting sigma plus and sigma minus light. So first resonant level excitation is done with pi plus h nu. When you use the pi light for the excitation and also h nu light using the microwave from the B1 magnetic field, then the excitation will be pi plus h nu, and this excitation is used to excite the Mj is equal to +1 level, and the de-excitation will be done from the from Mj plus 1 level in the form of sigma plus light. So de-excitation light will be sigma plus light. So this is first level of resonance. Resonance means that the level Mj plus 1 is excited and Mj plus 1 level is de-excited. So here Mj plus 1 is the resonant level. Now I am going to consider Mj is equal to minus 1 as the resonant level. So the second resonant level will be excitation using the pi transition and then the de-excitation to the Mj is equal to minus 1 level using the using induced microwaves as the field from the magnetic field B1. So B1 field provide a quanta h nu which can be used for the de-excitation from the Mj is equal to 0 level to the Mj is equal to minus 1 level. So the excitation to Mj is equal to minus 1 level will be done using the quanta pi and using the quanta from the magnetic field subtracted from this pi as pi minus h nu. And once the level Mj is equal to minus 1 is excited, then of course it will de-excite to the ground state using the transition represented by sigma minus 1 light, which is also circularly polarized light with the electric field perpendicular to that of the applied magnetic field. So you see that here I have indicated two resonant levels. So that is why it is a double resonant experiment. The two levels Mg is equal to minus 1 and Mg is equal to plus 1 level can be excited through excitation of Mg is equal to 0 level of the 3p1 state. So Mg is equal to 0 level of the 3p1 state can be used to excite the other two levels of the 3p1 state, which are Mg is equal to minus 1 and Mg is equal to plus 1. And the two levels which are Mg is equal to minus 1 and Mj, sorry, Mg, not Mg but Mj. So Mj is equal to minus 1 and Mj is equal to plus 1 can be de-excited to 1s0. That is why the process is known as double resonance techniques. And these two resonant levels is what I have explained over here. The small high frequency quanta h nu, which is used for the excitation of the upper and lower Zeeman levels of the 3p1 state. So Mj is equal to plus 1 to Mj is equal to 0 of 3p1. So the small frequency h nu quanta can be used to excite the Mj is equal to plus 1 level from the Mj is equal to 0 level. So the small high frequency quanta h nu can be used to excite Mj is equal to plus 1 level from the Mj is equal to 0 level of 3p1. And similarly, the same small quanta h nu from the applied magnetic field B1 in the range of a microwave can be used to excite the Mj is equal to minus 1 level of 3p1 from the Mj is equal to 0 level. And these two levels are detected via much larger light quanta. So you see that we are detecting the small separation between the Zeeman levels using a much larger light quanta, that is from Mj is equal to plus 1 of 3p1 to ground state 1s0. And similarly from Mj is equal to minus 1 of 3p1 to 1s0 level. So larger quanta can be used actually in order to determine the separation between the Zeeman levels. This gives a very high detection sensitivity of h nu. So you see that the H nu, that is the energy difference between these Zeeman levels, which is very small, can be measured very precisely using a larger quanta represented in green and represented by the sigma plus and sigma minus light respectively. And this measurement can be carried out very precisely. So the sensitivity of the system using the double resonance method in order to determine the separation between the Zeeman levels is increased through the method of double resonance technique. Now the detection of spin resonance in a short-lived excited state becomes possible. So you see that if these two states, for example, mj is equal to +1 and mj is equal to -1, if these states are very short-lived states, then of course even using a larger amount of spectra, that is a larger amount of transition, that is a sigma plus and a sigma minus, can be used in order to detect, in order to precisely measure the separation between the short-lived Zeeman levels. So the detection of the spin resonance in a short-lived excited state becomes possible. Double resonance method gained considerable importance in spectroscopy during the last 5 decades. So I am not next. I am also going to describe another experimental setup, which I shall be referring as the second double resonance technique. The first double resonance technique was defined using the mercury atoms or the mercury vapor atoms. And now I am going to define or describe another experiment for the second, which I am calling as second double resonance technique. And here I am using light from the sodium D1 line. So consider the transition sodium D1 line, that is the transition from 2s half to 2p half. So this transition is also a resonant transition. So you can put a double arrow between these two levels. So 2s1 half to 2p1 half is the transition which involved in the resonance of sodium D1 line. Now you see that this transition is in the absence of the magnetic field. So in the absence of the magnetic field, the ground state, which is the S1 half state, has only J is equal to 1 half level, is a single level, and similarly the excited state P1 half level has a value of capital J is equal to 1 half, which is again a single level. But when you apply the magnetic field, these levels will split into Zeeman levels. So when B0 is applied, the terms are split into Zeeman terms with the mj is equal to plus minus half, because both have a value of j is equal to plus half. For both these states, that is the ground state S half and the first excited state P half, both have the value of j is equal to 1 half. So under the application of the magnetic field, these j levels will have j degeneracy is lifted and then will split into mj levels. So mj levels will be plus minus half levels for both of these two, for both of these two levels, that is for the ground state level and for the first excited level, which is p half. So for the excitation we are using sigma plus line, that is a circularly polarized light will be used for the excitation from the minus half level of the 2s half, that is from the lowest of 2s half level, the transition is done to the upper Zeeman level of the 2p half level, that is mj is equal to plus 1 half of the p1 half level. So this is the excitation that we shall use using the sigma plus light. That is the transition using sigma plus circularly polarized light with the electric field perpendicular to B0 will be used in the excitation of the upper level of the Zeeman splitting. And you know that P1 half has two Zeeman levels, one will be represented by mj is equal to plus half, and the other will be represented by mj is equal to minus half. So we, and similarly, the ground state has two levels, mj is equal to plus half and mj is equal to minus half. So here the transition will be carried out from the mj is equal to minus half, that is the lowest mj level of the ground state, to the upper mj level of the upper state p half. And for that one, I shall be using the light, which is a sigma plus light. Now you see that I am going to show you the same experimental setup similar to the previous one, and here the cuvette contains sodium vapors or the sodium atoms. And you know that the coils of the magnetic field B1 are now shown, and also the coils of the magnetic field B0 are shown. The coils of the magnetic field B0 are shown in green, whereas the coils of the magnetic field B1 are shown in red. And you know that a circularly polarized light from the sodium lamp with the sigma plus polarized light is incident on the sodium vapors contained in the cuvette. And of course, the light will be the light from that one will be incident on the photomultiplier tube. This light may be used in the absorption spectroscopy. So the magnetic field B0 will be used to generate the Zeeman levels. That is, will be used to split the J level into Mj levels. So the ground state 1s half will be split into two mj levels. Similarly, the first excited state p1 half will be split into two mj levels, that is mj is equal to plus minus half, with the application of the magnetic field B naught. And the magnetic and the quanta from the magnetic field B1, which can be changed, that is a magnetic field B1 can be changed in frequency, and then of course the quanta of microwave from the magnetic field B1 can be used for excitation between the levels, between the Zeeman levels. In the presence of the magnetic field B0, the levels in the sodium atoms split into the Zeeman levels, represented by Mj is equal to plus minus half. The sodium sigma plus circularly polarized light is used for the excitation or for the absorption from the ground state. Mj is equal to minus half of S1 half to the upper level. Mj is equal to plus 1 of the P1 half level. So let me indicate, so let me show you this one. So for example, from this solid arrow with indicated with sigma plus will be used for the absorption or for the excitation of the mj is equal to plus half level of the 2p half Zeeman level. And the transition is done from the ground state, which is the minus mj is equal to minus half level of the ground state of the ground Zeeman level, which is of S1 half, which is and the ground level of the and the ground Zeeman level is mj is equal to minus half. So the transition is done from this level to the upper Zeeman level of the excited state. So let me read this paragraph again. In the presence of the magnetic field B0, the levels in the sodium atoms split into Zeeman levels with mj is equal to plus minus half. The sodium sigma plus circularly polarized light is used for the excitation or absorption from the mj is equal to minus half of S1 half level to the mj is equal to plus half of the upper level of the Zeeman level, which is mj is equal to plus half level of P1 half. The high frequency field B1 is used to induce the transition from mj plus half of 2s half level to mj is equal to minus half of 2s half level, and increases the population of the sodium atoms used for the absorption of input light. So let me explain the figure so that the things become clear. So you see that here I have shown B naught, that is the applied magnetic field is 0. When the magnetic field is 0, you can see that 2p1 half level is represented by a single level, and the ground state 2s half level is also represented by a single level. And these two levels are the resonant levels also. So when we apply moderate magnetic field, that is apply constant magnetic field B naught in the moderate range, then of course the single level with J is equal to 1 half will split into two levels with Mj is equal to plus half and Mj is equal to minus half. That is, the J degeneracy is lifted. Similarly, the J degeneracy is lifted for the S half level, which was the single level. So under the application of the magnetic field, this J level will be split into two Mj levels with the values Mj is equal to plus half and Mj is equal to minus half in the presence of the applied magnetic field P naught. And you see that we are using the transition or the absorption or the excitation we are using for the sigma plus line, used for the excitation of the lowest S half value to the upper Zeeman level, which is indicated by Mj is equal to plus half. And this transition is indicated by the red arrow. This red arrow will give you an optical transition and is indicated by sigma plus transition. Now you see that there are two ways that this transition from the sigma from mj is equal to plus 1 will decay to the lowest to the ground state. So it will decay using the green transition represented as pi transition to the upper level, to the upper Zeeman level of the ground state, which is mj is equal to plus half state of the ground level. And this will occur using the pi transition, and this is also an optical transition. The other transition will be sigma plus, that is also a resonant transition in resonance with the previous transition, that is from the mj is equal to plus half level to the mj is equal to minus half level of the ground state. So sigma plus and sigma plus have been shown as the resonant levels from the mj is equal to plus half level to the mj is equal to minus half level. But you see that the important here is the transition indicated as a pi transition and shown in green arrow. So this is the pi transition, that is from mj is equal to plus half to plus half level of the ground state. So you see that using this pi transition, we can determine the separation between the two lower Zeeman levels. That is the Zeeman levels with the mj is equal to plus half, and the separation between the levels with the mj is equal to minus half. That is the separation between these two mj levels corresponding to the ground state. Their separation indicated by with this blue arrow can be determined very precisely using the double resonance experiment and using especially the light emitted by the green wave, by the green transition. And the transition from the mj is equal to plus half level to the mj is equal to minus half level of the ground state will be through the electron spin resonance or the relaxation. This relaxation can occur either the sodium atom in this state, that is in the mj is equal to plus half state, collide with the sodium atom with the mj is equal to minus half state, and the energy is transferred. And the atom is de-excited, that the sodium atom in the mj is equal to plus half is de-excited to the sodium atom with the mj is equal to minus half, and the energy could be used maybe in the kinetic energy of the sodium atom. And the second option is that this mj is equal to half level will collide with the walls of the container. Here in this case, the walls of the cuvette and then de-excite that is the de-excitation will cover, because the energy of the sodium in the Mj is equal to plus half will be transferred to the container wall, and then of course that sodium atom will fall to the ground state, that is with the Mj is equal to minus half state. Now there is another option, which is the third option. The third option is what you can use the magnetic field B1 in order to induce the transition, from Mj is equal to plus half to the Mj is equal to minus half. So this transition can be induced using the magnetic field B1. That is, you provide a quanta h nu which matches with the energy of these two levels, then of course the transition will occur. And you know that this transition, that is the Mj is equal to plus 1 level, is populated through the pi transition. So using the magnetic field B1, when this transition will takes place, that is the electron spin resonance takes place, then of course the population of the ground level, which is the minus Mj is equal to minus half level of the ground state, will increase drastically. And then of course the absorption will increase. Using the absorption spectroscopy, we can detect this increase in the absorption, and through that one we can notice that the microwave energy is matching with that of the separation between these two levels, and noticing the value of the microwave provided by the B1 magnetic field, we can determine the electron spin resonance between the Mj is equal to plus half level and Mj is equal to minus half level. Emission occurs as a sigma plus circularly polarized light from Mj is equal to plus half of the P half level to Mj is equal to minus half of the 2s half level, which is shown, you see that again by the red line, that is the transition, that is the level Mj is equal to 1 has the two possible to decay. One is the decay through the red light, which is in resonant with the transition, with the absorption. So the emission will also takes place through sigma plus line. The second option is that the emission will takes place through the pi light, which is shown in green in this transition, which is also important for us over here in order to determine the separation between the two ground levels of these Zeeman levels. We can determine the separation between these two levels, that is the electron spin resonance separation can be determined using the pi transition. So the pi transition, which occurs from Mj is equal to plus half of the P1 half level to Mj is equal to plus half of the S half level. Now the relaxation of Mj is equal to plus half of the S1 half level to Mj is equal to minus half of the S1 half level occurs when the sodium collides with the sodium atom, or when the sodium collides with the walls of the container. These are the two options. But there is another option through the magnetic field B1. So if the relaxation by collision is slow, then it can be induced by irradiation by microwaves using the field B1. The electron spin resonance transition change the population of the Zeeman levels. Mj is equal to plus half of P1 half level by increasing the population of the lower ground state, which is Mj is equal to minus half level of the ground state S half level. So you see that using the spin resonance level, you can increase the population of the ground state, which is Mj is equal to minus half level of the ground level. Its population can be increased using the spin resonance transition, using the microwave quanta from the magnetic field B1. So when the magnetic field quanta from the magnetic field V1 is tuned, and when it matches with the separation indicated by the blue light, by the blue arrow, then of course the transition from Mj is equal to plus half will occur to Mj is equal to minus half. So the population of the ground state will increase. And of course, when the population of the ground state will increase, more atoms will be present for the absorption or for the excitation, and ultimately the population of the Mj level is equal to +1 will also increase. And through the absorption spectroscopy, we can measure this increase in absorption, and then of course at that time we can also measure the separation between the two levels indicated by the blue arrow. Detection of this electron spin resonance can be accomplished through the change in the intensity of the absorption from Mj is equal to minus half of S half level to Mj is equal to plus half of P half level. So during this process, the change in intensity can be observed provided the population of the ground state term was altered by optical pumping. So it is required that when you carry out the transition from Mj is equal to plus half level of the ground state to Mj is equal to minus half level of the ground state, this transition must be done optically using induced energy from the magnetic field B1. So this transition must be optical transition if you want to measure the separation between these two levels. So you see that optical pumping is required. And this optical pumping is actually the induced pumping provided by the magnetic field B1. You induce the transition from the level of Mj is equal to from the level of the upper level to the lower level of the Zeeman splitting of the ground state. That is from the Mj is equal to plus half to Mj is equal to minus half. This transition will be done optically using the magnetic field B1. The absorption of the circular polarized light B plus light and the emission of the same light, both represented by transition in the red form, one pair of resonance, and the absorption of the circularly polarized light sigma plus light and the emission of pi linearly polarized light along with the electron spin resonance form the second pair of resonance. Thus, the presented technique is an example of the double resonance method. So you see that I have explained the double resonance method using the sodium D1 line and also the first transition using the mercury vapors. And I have explained how the double resonance method can be used to precisely determine the separation between the Zeeman levels. So you see that this is the last lecture of the series in which the atoms were subjected to the applied constant magnetic field B naught. So you see that in this series of lectures where we applied the external magnetic field, we measured the normal Zeeman effect, which is called ordinary Zeeman effect. We described the anomalous Zeeman effect. We described the push and back effect, and we also presented the case of double resonance method for the determination of the separation between the Zeeman levels. So this is the end of slide number 13E of the course on atomic and molecular physics.